So the sort of title of this video is conservation of momentum. And so we're going to look at what that means and how you will apply it. Now, that term conservation you've met before in terms of energy back in year 9. And if you remember, it just means staying the same essentially. So this means that momentum stays the same. Now we are looking at very specific context here. Okay, so we are looking at something called a closed system. Now, a closed system just means no external forces act. So in other words, we're just looking at two objects, or more, but normally two objects, either colliding together or moving apart, and we're just looking at those two objects. So we're not worrying about friction and things like that. So we're not looking at any external forces. And our rule simply says this, that the total momentum before an event is the same as the total momentum after the event. So, for our first examples then, in fact, we'll probably kind of use these for a couple. We're going to think about some vehicles colliding. And so I've got a truck. Okay, I'm going to have to put it as a sort of plan view. So there's my truck. And I've got a quad bike. So we'll put the quad bike down just here. Now we're going to need some numbers on this in a second, but let's just imagine what is going to happen if we'll say that the quad bike is stationary to start with, but this truck comes along and collides with the quad bike. Now this truck has got momentum. It's got momentum to the right as it moves along like this, and that means that after the collision, whatever happens, there must be momentum to the right. So there are a few different options. Of course, what could happen is that the truck hits it and stops, and all that momentum is transferred into the quad bike, and the quad bike moves off like this. We may find that the truck comes along, hits the quad bike, and they join together and moved off like this. Probably the more likely situation, to be honest, assuming again, because there are no external forces, we're not worrying about kind of impacts and things crushing. But probably the more realistic situation is that the truck hits the quad moves off, and the truck carries on moving as well, but slower, because some of the momentum of the truck has passed into the quad bike. Let's look at a couple of examples then, putting some numbers into it, just so you can see what's going on. So what we'll say is that our quad bike here has got a mass of 500 kilograms. Okay, and we'll say that our truck here has got a mass of 2,500 kilograms. That's about right for a pickup like that, 2.5 tons. And we'll say that our truck here is going to be moving at the start at 2 meters per second. And we'll start off with that simple case. Let's start off by saying that when it collides, the truck stops and the quad bike starts moving. So what I'm trying to work out is the speed v which the quad bike moves after the collision. Okay, so it's stationary to start with, then we're looking at how it moves. So we're basically looking at this situation. Truck comes in, hits the quad bike, truck stops, and off goes the quad bike. What speed does it move at? Okay, now my starting point is always the same for questions like this, and you'll get fed up of writing this out, but it's important to do it in every question because it shows you're working clearly. Obviously, if at any point you want to pause the video to copy stuff down, that was a really good idea. Feel free to do that. So momentum before the collision equals momentum after the collision. Okay, hopefully you can read that okay. Now, let's put some numbers in then. Momentum before the collision. Well, the momentum of my truck, 2,500 times 2. Mass times velocity, remember, for momentum. Now, I'll put it in here, but we don't really need it. In fact, I'll put it in red to show you that it's kind of optional. Momentum of the quad before, well, just plus 0 because it doesn't have any momentum before the collision. So you can add it in just to be complete. I'll show it there, but don't feel you have to. Now, after the collision, the truck has stopped. So again, well, what's the momentum of the truck afterwards? It's 0. So again, we don't really need to write it in, but I will just to show you where these numbers are coming from. Plus momentum of the quad afterwards. Now, momentum of the quad afterwards, well, mass, 500, times the velocity, which is v. That's what we don't know what it is, so that's what we're trying to work out. Okay, you can just write that out as velocity if you want to. Okay, 2,500 times 2, that's 5,000. So 5,000 kilogram meters per second, that's the momentum before this collision. That's how much momentum my truck has got. okay, equals 500 times the velocity v. So I've got 5,000 equals 500 times v. Now remember this, we've got marks by now, we've put numbers incorrectly, so just think maths, 5,000 equals 500 times v. That means that our velocity is going to be 5,000 divided by 500, which is obviously 10 meters per second. Okay, now you might be thinking, well, why does the quad end up moving quicker than the truck did to start with? Well, the reason is because the quad has a much smaller mass. So although the momentum is the same before and after, the quad goes quicker because it's got a smaller mass than the truck did. Okay, you can see then I've got rid of a few of the numbers there because I'm going to look at a slightly different example. What we're going to say now is that our truck arrives like this and it collides with the quad. But instead of the truck stopping, they now actually move off together. So they kind of join together. Now, before we worry about the numbers, let's think about what we would expect. Well, we would expect to see that there's a smaller velocity afterwards than there is at the start, because essentially the mass has gone up. Okay, if we go back to our original sort of definition there, you can see total momentum before is total momentum afterwards. So let's look at another similar example. Okay, let's think about some astronauts. There's an astronaut, the other astronaut collides with it, and you can see that they move off together, but they move off slower than the astronaut was moving at the start, and that's because the overall mass has gone up because they've joined together. We can look at another stupid example here. Okay, it's two fish, okay, and you can see that they move off together. Okay, back to our truck and quad bike. We're going to have this collision, and we're going to try and work out again the speed afterwards, but this time when they join together. Now, momentum before, well, that's still the same. That's why I haven't bothered to rub it out. Momentum before is still 2,500 times 2. No momentum of the quad bike, giving me 5,000 meters per second. But momentum afterwards, let's think about that. Well, the mass afterwards has changed. Because they've now joined together, my mass afterwards is now going to be 3,000. Okay, because these two join together, 2,500 plus 500 gives me that 3,000 times my velocity. So what I've got then, I've got 5,000 equals 3,000 times v. So that means this time my velocity afterwards is going to be 5,000 divided by 3,000. Okay, and if you work that out, that gives you about 1.7 meters per second. So like we predicted, that's a lower velocity than the truck had to start with because they've joined together and so the mass has gone up. Now I suppose we should really, and I should have done it in the last one, be making sure we remember to put a direction on these because it is a vector. Remember, momentum does have a direction and so does velocity. This is a velocity, so we need a direction on there. Right, okay, for another example then, this isn't the other common situation. We've talked quite a lot about collisions there, but now let's think about explosions, or when things move apart. Now the context I'm going to use here is one of many that they could use, but you can see I've already got drawn on my board there. We've got the land here, and we've got some water here, perhaps the sea. And here is Mr. Braxton. There he is. And Mr. Braxton is going on a boat. There's the boat. Here's Mr. Braxton. So it's nice to have a little extra danger there as well. So Mr. Braxton's in his shark-infested waters on the boat, and obviously he wants to get onto the land. So he rows his boat up to the land, and then he jumps off. Now, you just think logically about what's going to happen here. You probably know this, that if Mr. Braxton jumps onto the land, the boat will move backwards. It's the same idea if you jump off a skateboard. The skateboard will often move the opposite direction. So we need to think really about why that is, and it all comes back to momentum. If you think about it, at the moment, the overall momentum is 0. Okay, and in fact, I'm going to write that up here because we are going to need that fact later. The total momentum before Mr. Braxton jumps is 0. Okay, because nothing's moving. He's not moving, the boat's not moving. And so because of conservation of momentum, once he's jumped off the boat, the total momentum must still be 0. So as Mr. Braxton jumped this way, giving him momentum forwards, in order to give me 0 momentum overall, the boat must move backwards with the same momentum. Okay, let's put some numbers into this and we'll do a quick example just to see how this works. So I'm going to say that the boat is 700 kilograms. Okay, and I'm going to say that Mr. Braxton is 70 kilograms. Now obviously Mr. Braxton ends up moving to the right, the boat will end up moving to the left. So let's say that Mr. Braxton jumps with a velocity of 2 meters per second. Okay, and so what I'm trying to work out is the velocity v which my boat moves backwards with. Okay. Now there are 2 different approaches to this. I'll give you the slightly more straightforward approach first, and then look at the more mathematical approach, which is great if you're a bit more confident with maths. Let's just look at this in a way that hopefully all of you will understand. I need my total momentum to be 0. Okay, which means that whatever momentum Mr. Braxton has forwards must be the same as the momentum the boat has backwards. So let's look first of all then at Mr. Braxton's momentum. So his momentum is mass, which is 70, times his velocity, which is 2. That gives me a momentum of 140 kilogram meters per second forwards. So that means the boat must have 140 kilogram meters per second backwards, because the momentum's got to be the same so that the total is 0. So mass is 700 times the velocity, which is what we're trying to work out, must still give me 140. The only difference is that it's moving to the left. Okay, and so that means then the velocity v is 140 divided by 700, and that gives me an answer of 0.2 meters per second. And we know then that that is going to be to the left. Now you might be thinking, well, why does the boat move backwards so much slower than Mr. Braxton jumped forwards? Same idea as we had before. The boat is a lot heavier, it's got a much higher mass. Therefore, if it's got the same momentum as Mr. Braxton, because the mass is bigger, the velocity is smaller. Okay, now I said that I would show you the slightly more difficult way, so let's look at that now. Let me just get rid of this. So this is the slightly more mathematical way, and it's going to be using exactly the same procedure as before. So I'm going to start off by writing momentum before, if I've got space, equals, squash it up a bit, momentum after. Okay, right, momentum before, that's easy, we know that's 0. Equals, right, momentum after. So let's work out Mr. Braxton's momentum first of all, just like we did a minute ago. We've got 70 times 2, plus, I want the total momentum, so plus the boat's momentum, which is going to be 700 times v, which is the velocity the boat is moving at. Okay, so let's just sort out these brackets. So 0 equals 70 times 2 is 140, plus 700 times v. Now, imagine you're in maths and you have this as an equation. I'm going to take 140 away from both sides. So minus 140 equals 700v. Obviously, if you want to pause the video to slow it down and check each step, by all means do that. That means my velocity is minus 140 divided by 700, which is minus 0.2 meters per second. Now you can see my number's the same as I got before, which is what I would expect. What does this minus mean? Well, the minus is telling me that it's going to the left. Okay, and so that has given me my answer. It's minus because it's moving to the left, telling me it's in the opposite direction.